Okay, so we have seen how star does the mapping. What's different when you map with HiSet2? Well, HiSet2 was created by the same people who also created Bowtie. So HiSet2 is very much based on the algorithm and the method that Bowtie uses. So for instance, it uses the same method to compress the reference genome so that it fits the memory of your computer. It uses the same way to create an index, but on top of that global index of the complete genome, it creates thousands and thousands of small indexes that will allow for the gaps in the alignment. Because of course, Bowtie is a DNA-seq mapper and it cannot handle gaps in the alignment. So that's the big change in HiSet2 compared to Bowtie. It creates additional smaller indexes that allow to create gaps in the alignment. So remember what I told you previously, when a read maps over an intron, it consists of two anchors. So each anchor is the part of the read that map at one side of the intron. So what will HiSet do? It will map the largest anchor on the global index on the complete genome. If the majority of a read maps to the complete genome, but a small part of the read does not map there, then HiSet will try to see if that read might map over an intron. How? Well, the mapping on the global index on the complete genome will tell HiSet which local, smaller indexes he needs to try, and then he will try to map the remaining part of the read on these local, smaller indexes. The alignment itself is very similar to the method that BLAST uses for creating alignments. So basically what happens is a score is calculated for each alignment, and that score is calculated by adding scores for the matches in the alignment and by subtracting penalties for mismatches and gaps. If the total score of the alignment is higher than a certain threshold that is set, then this alignment will be considered valid and it will be reported. It will be added to the output file. With respect to introns, HiSet has more or less the same parameters as star. So you have to tell HiSet how large the gaps in the alignment can be. And how long can they be? Well, they can be the size of an intron. Just as was the case for star, the default setting for these maximum intron sizes is ideal for higher eukaryotes, but when you work with a more simple organism, you have to adjust them. So let's take a look in Galaxy. So in the tools section, you simply type HiSet2. That will take you to the parameter form. Most of the parameters will be very similar to the parameters for star. So I will not go over all of them. For instance, the BLAST-like parameters, so the scores for the matches in the alignments and the penalties for the mismatches and the gaps, can be found here in the scoring options. I never changed them, I have to be honest, but I can show you that they were there. So you have the mismatch penalty. And as you can see here, you can also set penalties for soft clipping. You can also completely disable soft clipping. Star also allows that, to disable the soft clipping. But on top of that, HiSet also allows you to do soft clipping, but to penalize it. Well, it's always penalized a bit, but you can increase the penalties. And here you have penalties for gaps, opening, extending gaps. Okay, here under reporting options, I also want to show you this part here, the primary alignments. So what is this about? Well, that the value for this should be a number, and that number reflects the maximum number of distinct primary alignments that HiSET will search for each read. So what are distinct primary alignments? Well, distinct means that they should all map to different positions in the genome. And primary alignments mean that from all the alignments for that read, the primary alignments are the ones that have the highest score, the highest alignment score. So you can have one alignment with the highest score, then you have one primary alignment. You can have multiple with the same highest score, and then you have multiple primary alignments. So this parameter here allows you to set a maximum for this. It will define the maximum number of distinct primary alignments that are reported for each read. Now, you have to take care of this parameter because HiSET will find alignments in a random order. So, and if it has found k distinct primary alignments for a read, it will stop searching for further alignments. And there's no guarantee that the k primary alignments that are found at this point are the best alignments. It might be that there is an even better one with a higher alignment score that has not yet been found. And then also worth mentioning are here, scrolling up again, the summary options. So the options that I have shown were all advanced options. You also have summary options. What is important here? Well, this one, the print alignment summary to a file. I always put this one to yes because it will create a file that looks like the log file that is generated by STAR. So a file that contains the summary statistics of the mapping. Output of HiSET2 is always a sum file. On the slide, you will find a link to the manual of HiSET2 that will allow you to take a look at all the other parameters. So